So good afternoon, everybody. I'm extremely happy to welcome in our AI seminar series here at TII, Maxime Vono, who's a postdoc researcher in the Lagrange Mathematics and Computing Research Center in Hawaii, Paris. Maxime has been working for many years in the topic of machine learning and has focused in the last years on the topic of federated learning and especially Bayesian federated learning. As many of you know, there's a big shift today towards basically cloud AI, towards more distributed AI mechanisms. And federated learning in terms of providing the ability to do some kind of collective intelligence out of individual intelligence has become extremely important. So I invited Maxime Vono because his recent work has a lot of good application today in the topics related to telecommunication, and especially understanding basically the right kind of algorithms that take into account the bandwidth constraints in terms of leveraging basically the huge amount of small databases which are spread across sensors, smartphones, and basically to be able to create some kind of aggregate models to work that. The work he's been doing has been jointly done with Aymeric Dieuleveult, who is working at École Polytechnique, Alain Durmus, who works at École Normale Supérieure Paris-Saclay, Eric Mouline, who's also professor at École Polytechnique, and Vincent Placier, who's actually now a PhD student at Hawaii and also the Lagrange Mathematics and Computing Research Center. So Maxime, the floor is yours, and you can start your seminar.
Okay, thank you, Marwan, for this kind introduction. So in this talk, I will present you my most recent research work, so namely a novel algorithm in order to perform Bayesian inference under the federated learning paradigm. So I think that most of you are quite familiar with Bayesian inference, but regarding actually federated learning, which is quite new, it might not be the case. So to this end, I will first present what we mean by federated learning before focusing actually on the proposed methodology. So to begin with, as you all know, training machine learning algorithms requires the availability of a so-called training dataset, which is made of examples such as features and labels for supervised classification, for instance. In traditional machine learning, actually, this training dataset might be very large and is classically stored in a single location, such as a central server. However, in real-world settings, data are not centralized in a single place, but are rather stored in local places depending on their own sources. So these different sources might be sensors, mobile devices, browsers, organizations, or even hospitals. And then the natural question is to wonder if we can centralize all these different sources of data in a single place, such as a central server. So interestingly, the answer to this question tends to be quite negative nowadays, because of three main reasons. So first, data might be too sensitive. So for instance, you can think about an hospital which owns some brain images of its patients in order to detect brain tumors. So obviously, these images are very sensitive and cannot be shared with a cloud server or even with other hospitals. Secondly, data collection in a single place might be too costly for two main reasons. So a limited upload bandwidth and power, and large local datasets. So you can think about, as an example, of self-driving cars, which are expected actually to release several terabytes of data per day, which will be very difficult to upload to a central location, such as a base station. And finally, there is also a growing user awareness and regulations on data privacy via, for instance, the General Data Protection regulation, so GDPR, which is a European regulation in order to protect data privacy. And in the computational advertising industry, for instance, these concerns about data privacy led to limitations regarding the use of third-party cookies and reflection of more private alternatives via the so-called privacy sandbox, which has been proposed by Google. So we saw that we cannot centralize local data. Then can we instead train a local machine learning model only using this local data? So in theory, this is doable, but there are several drawbacks associated to this local learning strategy. So firstly, the dataset might be too small, and as a consequence, might lead actually to poor generalization performances on unseen data. In addition to be too small, this local training dataset can be biased, meaning that the local data distribution is very different from the true data distribution. So this effect is actually called data heterogeneity in the federated learning community and might come from several factors such as different marginal distributions of features or labels. So in order to address all these issues, a novel machine learning paradigm referred to as federated learning has been recently proposed by Google researchers around 2017 roughly. So federated learning actually is a machine learning setting where you have multiple entities, which are called clients, such as mobile phones, which collaborate with each other in order to solve a common machine learning problem under the coordination of a central server, so a central entity. And instead of performing local training, these clients actually collaborate by exchanging some messages, such as model updates or gradient information, via the central server, which aggregates all these messages, update them, and then broadcast an updated information to the clients. And under this framework, you can see that local data are not exchanged, which allows to meet some kind of first-order privacy guarantee. So the federated learning is quite great regarding data ownership issues, so that you actually keep, so that actually each client keeps its own local data set, but it is also associated with additional and new challenges. So in this slide, you have actually 5 main challenges that might occur in federated learning, but it is actually non-exhaustive. So the first one actually is the communication bottleneck. So you saw that federated learning assumes communication between the clients and the server. And actually, in order to have a communication and efficient algorithm, you have actually to ensure that the communication between the clients and the server is quite efficient. You might also have some local data sets. So if you think about organizations or hospitals, that might be quite large. So you have also a computational bottleneck in updating and calculating the gradient information locally. Also, and contrary to actually the classical distributed setting, the clients actually might be unreliable, such as in cross-device settings. So you can think about mobile phones, and actually some mobile phone might be switched off. And so they cannot participate in each actually communication round. So this is called partial device participation and is actually an additional bottleneck which comes from the federated learning paradigm. You also have the personalization bottleneck actually. So clients do not have enough data in order to learn a global model which generalizes well on unseen data. But once you learn a global model, actually each client wants to adapt this global model to its own local data distribution in order to perform personalized inference. So this can be related to multitask learning, meta learning, one-shot learning, and it is actually left for future works and will not be discussed in this talk. Also, so you saw that federated learning meets a kind of first-order guarantee, privacy guarantee, by not exchanging local data between the clients and other clients and the server. But basically, this is not enough, because if you actually communicate some gradient information or model update, you implicitly have some data information in this update. And in order to have more secure communication between the clients and the server, so you have other works based on differential privacy, homomorphic encryption, secure aggregation procedures, etc., that will not be discussed in this talk. So actually in this talk, I will discuss about the first 3 points. So I will address the communication bottleneck, which has been emphasized by Merwan at the beginning of this presentation, the computational bottleneck, and the partial device participation scenario. So to this end, actually, I will formulate the problem as follows. So I will assume that I have a central entity, a central server, capital K clients, and each client actually owns a local dataset, capital DK, which is of size capital NK. And then under this framework, federated learning actually aims at solving the following problems, which is actually a weighted empirical risk minimization problem, where the weights are proportional to the ratio of data each client has, and the local empirical risk function is the same as the one you can find in classical machine learning algorithms, where you have here a function UKI, which can be a regularized loss function, for instance. So as in machine learning, except that you have a mixture of local empirical risk function. In order to solve this weighted empirical risk minimization problem, actually a simple but quite seminal algorithm has been proposed by Google researchers in 2017, which is called federated averaging. And actually, federated averaging does the following steps. So you assume that you have a current update of the parameter of interest theta on the central server. So the central server broadcasts theta to all the clients. So basically, here for simplicity, I do not assume partial participation, but it can be actually generalized to partial participation. So the capital K client has theta, then perform a local gradient descent step. So in this slide, actually, I assume that each client performs capital L local steps in order to bypass the communication bottleneck. Because if you actually only assume that each client performs a single gradient descent step, you have to communicate with the central server at each iteration, which is not feasible in practice because of communication constraints. So in order to bypass this problem, actually, you allow each client to perform multiple steps in order to communicate only periodically with the central server. Then each client uploads an updated parameter theta k to a server, and the server performs averaging, where the weights are again proportional to the ratio of data each client has. So this is federated averaging, and I will in particular focus on the communication bottleneck, which will be very important in this talk. So you saw that in federated averaging, the communication bottleneck has been addressed by only communicating periodically by performing multiple local steps. Actually, you can also find another complementary approach in order to tackle communication, which is the use of compression operators. So basically, you will do one local step, but in order to reduce the number of bits you transmit to a central server, actually, you will compress the message sent by each client with a compression operator. So this has been proposed in 2017 by Alistair and co-authors. And the proposed approach is called quantized stochastic gradient descent. So obviously, there are numerous extensions of these two seminal works, such as Scaffold, Diana, Artemis, which actually improve upon Convergence these two algorithms. So if you want more information, I'll let you actually see and read the following review paper on federated learning. So I will now dive in the Bayesian perspective. So from a Bayesian perspective, actually, you have most of the efforts that have been put on federated distributed approaches have considered actually a communication scheme which is not based on gradient compression. So as an example, you have here a non-exhaustive summary of distributed Markov chain Monte Carlo algorithms, which actually you have three classes of algorithms. So the first type is called one-shot. So basically, on each client, you run independent and in parallel Markov chains in order to sample from a local poster distribution, and then you aggregate on a central server actually these local samples in order to have samples from a target global poster distribution. You also have distributed variants of so-called stochastic gradient Langevin dynamics and global consensus approaches, which are actually algorithms, Bayesian algorithms, which update the parameter of interest based on federated averaging type updates. And we proposed actually a work last year, which has been accepted at ICML, which belongs to this class of global consensus approaches, and where the communication bottleneck has been addressed with multiple updates, as in federated averaging. So here in this talk, I will propose you another scheme, another Bayesian scheme, which is this time based on compression. And the aim actually is to compare this compression-based Bayesian algorithm with other Bayesian algorithm based on other communication schemes, such as multiple local steps on one-shot approaches. So you have in this table actually a non-exhaustive summary of the current existing federated Bayesian methods, where I highlight actually in the last 3 columns if each method actually tackles data heterogeneity, the partial participation scenario, and if the approach actually involves some theoretical guarantees on convergence. And basically, we proposed actually we meet all these constraints in the paper we submitted this year actually to ISTAT conference. So I will, in this talk, I will present this approach and give you several insights. So first, I will present you the Bayesian federated learning approach based on compression, so which tackles the communication bottleneck via compression of gradients, which are sent by each client. I will show you that this approach can be robust to data heterogeneity, and it can be shown actually to encompass the partial device participation scenario. I will then present you some theoretical convergence analysis by showing you the impact of dimensionality, partial participation, compression, and stochastic gradients on convergence, before finally showing benefits with numerical experiments of the proposed methodology on several federated learning benchmarks. So if you have any question in this at this point of the presentation, so do not hesitate. Otherwise, I will begin with the presentation of the proposed methodology. Okay, so if this is okay, so I will first present the proposed methodology. So a quick recap on Bayesian inference. So we assume this time that we have a global dataset capital D, that the parameter of interest theta is now a random variable, so it is an unknown object of interest. I will put a prior on theta, and based on the data I have, I will define a likelihood function, update my prior belief with a Bayes rule, and end up with a so-called Poster distribution in green. And then based on this Poster distribution, I will be interested in calculating key quantities such as Bayesian estimators and credibility regions. And so you can see that actually these 2 types of key quantities I want to calculate can be actually formulated as integrals with respect to the Poster distribution. So in practice, actually, these integrals are very high dimensional and cannot computed in closed form. And what we do in practice, so there are many schemes to approximate integrals. So one scheme we consider here is to perform Monte Carlo integration. So basically, I will transform the computation of an integral into the computation of a finite sum, which involves some samples, theta t, which are drawn from the target Poster distribution. And so I transform an integration problem into a sampling problem. And now I will be interested in deriving actually efficient sampling strategies in order to draw these theta t, these samples from the Poster distribution. And an application of this Monte Carlo integration scheme is actually Bayesian model averaging in machine learning. So regarding Bayesian federated learning, so we saw that classical empirically risk-based federated learning actually aims at solving the following at the top of the slide minimization problem. And regarding actually under the Bayesian paradigm, we are interested in sampling from a target posterior distribution, which can be expressed as the product of capital K local Poster distribution. So why introducing now local Poster distribution is that actually each client has a local data set. So I can define a local likelihood function, put a common prior distribution on the parameter of interest theta, and define a local Poster distribution. And then I just say that the global Poster distribution of interest is just the product of this local Poster distribution. And I will assume an exponential form of this local and unnormalized Poster density function for each client, where UK is called the potential function. And in order to sample from this target Poster distribution, I will consider the most popular sampling approach in machine learning, which is called Langevin dynamics. So basically, Langevin dynamics is based on a stochastic differential equation, so SDE, which is actually formulated in the middle of the slide in the orange box. And actually, under mild assumptions. So this SDE can be shown to admit the target posterior distribution as invariant measure. And this is why actually we use Langevin SDE to target the posterior distribution because of this guarantee. But in practice, actually, especially in a high dimensional scenario, we cannot simulate continuous path following this Langevin stochastic differential equation. So in practice, what people do is that they consider a discretization scheme of this Langevin stochastic differential equation. So a common one is the Euler discretization scheme, which is formulated at the bottom of the slide, where I introduce here a scalar discretization parameter gamma in red. And because of this discretization parameter gamma, actually, I do not target the posterior distribution pi of theta given d, but now I actually target an approximation of this posterior distribution because of this discretization error. So this is called actually Langevin dynamics, so the last one. And for those who are not familiar with Langevin dynamics, actually, if you remove the Gaussian noise in the Langevin update, you retrieve actually gradient descent. So Langevin dynamics actually is like gradient descent with Gaussian noise. And actually, it has been very highly used in machine learning because of this simplicity, is that actually by just using, if you know gradient descent, you know how to perform Langevin dynamics actually by just adding standard normally distributed noise actually. So very simple to do in practice. So in practice, actually, if I want to implement Langevin dynamics in the federated learning context, I will do this. So first, given a current iterated theta t on the central server, I will broadcast theta t to all the clients. And then each client will have to compute a local gradient at theta t. However, as I said, actually, if I have a large organization or large hospitals, etc., the local dataset, the size of a local dataset might be large, and calculating this local gradient actually has a cost which is linear with respect to the size of a local dataset. So to address this computational bottleneck, actually, I will first consider stochastic gradients and then send this stochastic gradient to a central server. However, if I do this, I have a limited upload bandwidth. So in order to address this communication bottleneck, I will consider sending actually compressed version of this local compressed stochastic gradients. And then I have also to tackle the partial device participation scenario where only a subset of the capital K clients actually send to a central server these gradient information. So to do this, I will just change the following Langevin update by considering actually that only a subset of active clients will send this local gradient information. And I have a weight actually in front of the sum in order to have an unbiased estimate. So I will now focus on the update in orange actually, which is this one, which is called Quantized Langevin stochastic dynamics for federated learning. And this is actually the algorithm we proposed in our ISTAT submission. And it has actually two main ingredients, so namely local stochastic gradients HK and an unbiased compression operator C. So I think that most of you, if you are familiar with stochastic gradient descent, you know what are local stochastic gradients, but regarding actually compression operator, it might not be the case. So I will give you actually in the following slide an example of a compression scheme which has been used in federated learning. So again, this to make a link between sampling and optimization, if you remove Gaussian noise in this QLSD update, actually you retrieve QSGD, which has been an optimization, which is actually an optimization algorithm which has been proposed in 2017 to address federated learning from an optimization point of view. So regarding compression, actually, you have here an example of a compression operator, so which takes as input a vector v, which lives in RD, such as a gradient, and it has as a parameter the number of quantization levels s, which is an integer parameter. And it performs actually compression component-wise. So for each coordinate of this vector V, I will compute this ratio of the absolute value of Vi over the norm of V, see where this ratio falls between 0 and 1, and then draw a Bernoulli random variable. And depending on the value of this Bernoulli random variable, I will affect this ratio to the bin L over S or to the bin L plus 1 over S. And basically, by doing this, I perform the quantization or compression of this coordinate Vi with the following scheme. So basically, the compression scheme will equal actually the norm of V times the sine of Vi times the bin, where this ratio actually has been affected. And from a communication point of view, basically, I will have to send to the central server a real scalar value. So basically, the norm of V times the sine of Vi, and an integer, so L plus 1 or just L, to the central server. And with the use actually of Elias encoding, I have in expectation some guarantees in terms of expected number of bits which are communicated to the central server. So as an example, if I take the number of quantization levels S, which equals square root of D, where D is the dimensionality of the vector I want to compress, I have in expectation that the number of transmitted bits is roughly of the order of 3 times the dimensionality, contrary to 32 times D bits if I don't compress actually the vector V. So I have, in theory, for this particular value of the number of quantization level, an efficiency of 10 times, which actually motivates us to use this compression scheme in order to address the communication bottleneck. So this was actually the presentation of the proposed approach, so QLSD, which uses this compression operator and which actually considers compression of gradient updates. I will now show you some theoretical convergence guarantees for this scheme. So basically, I will make some assumptions. So first on the compression scheme, so we'll assume that this compression operator is unbiased, and I will have a sort of bound on the variance of this compression operator, which is, for instance, satisfied for the stochastic quantization scheme I just presented to you in the previous slide. So actually, you have a specific value for the scalar parameter omega based on the dimension D and the number of quantization level S. I also have some assumptions on the stochastic gradients, HK, on the potential function of the local Hausser distribution UK. So I assume that I will be in the strongly convex and gradient Lipschitz scenario. And to model the partial participation scenario, I will assume that each client has some probability P to be active at each communication round. And basically, in order to monitor convergence for this Markov-Chain Monte Carlo algorithm, I have to consider convergence in terms of distribution. So I have to consider basically the convergence towards the target poster distribution pi. And to do this, I will measure in Wasserstein distance of order 2, the distance between the marginal low of theta t, which is my update at iteration t, and the target poster distribution pi. And basically, I have the following explicit bound, which involves actually 2 terms. The first one in blue is a contracted term, which involves gamma, which is the discretization step size in the Langevin dynamics updates, and M, which is actually the strong convexity parameter of the local potential function UK. And basically, if I choose gamma, the discretization step size, to be sufficiently small, I can ensure that this term will contract towards 0 when the number of iteration t tends towards infinity. However, I will have another term in red actually, which does not actually vanish when the number of iteration t tends toward infinity. So basically, this term involves all the sources of errors I considered in QLSD. So the first one is the discretization error of the Langevin SDE. The second one is the use of stochastic gradients, which might have actually a large variance. And you can see that actually the variance is proportional to the square of the size of a global dataset. I also have the impact of the on the use of a compression operator and the impact of partial participation. And basically, I want to tackle two sources, two terms which slow down quite drastically convergence, so namely the variance of stochastic gradients. So we can see that actually the size of a global data set is quite huge. Actually, you have a very large variance and you actually have a dependence with respect to the square of the size of a global data set, which actually prevents from quick convergence for this algorithm. And you also have, so the second point, the terms that reflects actually data heterogeneity. So I will tackle these two sources of terms that slow down convergence with so-called control variates. So basically, I propose now two variance-reduced versions of the proposed methodology QLSD to address these issues. The first one is called QLSD star. And basically, the main difference with QLSD is to consider another local stochastic gradient, which has the following form, so in the middle of the slide, in the orange box, and which differs actually by a term in blue with respect to the standard local stochastic gradient, which has been used in QLSD. So basically, I just consider this. And so this new local stochastic gradient actually allows to reduce the variance of the stochastic gradients, but also you can see that actually this local stochastic gradient is not unbiased. So basically, if you take the expectation of this local stochastic gradient, you do not end up with the gradient of UK. And basically, it is a deliberate, actually, so a deliberate choice to do this. And it allows actually to remove completely the dependence on data heterogeneity for the convergence of this algorithm. But basically, you see that actually the use of this specific local stochastic gradient requires to have and to estimate the theta star, which is the minimum of the global objective function. So basically, you have to launch in a pre-processing step a federated learning algorithm in order to estimate theta star. So this is quite infeasible in practice. So in practice, we propose another version of the proposed algorithm, so QLSD++, which actually estimates theta star on the fly. So basically, it has two main ingredients. So first, it reduces the variance of the stochastic gradients with some control variate techniques by considering the control variate cite, and basically cite will tend toward theta star. So basically, you estimate on the fly theta star. But actually, this choice for the local stochastic gradient is not sufficient to remove the dependence on data heterogeneity. So to tackle data heterogeneity, we introduce a so-called memory mechanism. So instead of compressing this local stochastic gradient HK, basically we compress HK minus a memory term, so eta KT, which is a type of memory mechanism in order to remove the data heterogeneity. And basically, the final update of QLSD++ is this one. So I compress GK of theta t, and I just add all the memory terms to the global gradient update. So this is QLSD++. And by doing this, I can reduce the variance of stochastic gradients and remove the dependence on data heterogeneity for the convergence bounds. So basically, in short, in summary, you have at the top the bound I obtained with QLSD, and at the bottom, actually, an improved bound with better dependencies with respect to the variance of stochastic gradients. So now it is capital N and not square of capital N, and you don't have a term which depends on data heterogeneity. So you expect actually that this improved version for QLSD will converge actually more quickly actually. So in summary, the standard QLSD approach I propose actually suffers from high variance of stochastic gradients and from what is called data heterogeneity. And by improving QLSD with control variates or variance reduction techniques, I end up with stochastic gradients with reduced variance and no dependence on data heterogeneity. So that's the take-home message for the proposed approach. And I will now show you some benefits on several federated learning benchmarks with some numerical experiments. So I make a short break if there is any question regarding the theoretical part. Okay, so I will go on with the numerical experiments. So basically, I first show you a toy Gaussian example in order to understand the key components of the proposed approach. So I consider an artificial data set where I have capital K equals 20 clients. I am in dimension D equals 50. And I show you here with a 2D projection of this global data set, the data heterogeneity. So you can see that actually the color refers to each client. So you have 20 clients, 20 colors. And you can see that actually the local data distribution, which are all Gaussians, are different. So basically they have roughly the same standard deviation, but they have actually different means. So this is why this is an illustration of what I called before data heterogeneity. So I consider this framework. So where the likelihood function, the prior, and the global Poisson distribution are Gaussians. And I launch basically two instances of QLSD. So QLSD sharp with standard stochastic gradients and QLSD star with control variate theta star. And basically you have in brown and purple the updates of QLSD sharp, which is QLSD with standard stochastic gradient with different number of different value for the quantization parameter S. And we expect basically by increasing the number of quantization levels to increase actually the accuracy of the algorithm. And you can see that actually this is not the case, is that actually by increasing the quantization level to 2 to the power 16, contrary to 2 to the power 4, actually we end up with the same mean square error for a given test function. And basically, this is due, actually, this highlights the large impact of the variance of stochastic gradients, which actually dominate the variance of the compression scheme. And basically, by doing variance reduction, actually, we can see that actually this helps, is that actually, if I increase the number of quantization level, the mean square error actually decreases, as expected, because of the use of variance reduction, which helps in decreasing the impact of the variance of stochastic gradients. So this is actually very important in practice. And basically, I compared also QLSD star, so with 3 different number of quantization levels, so 4 bits, 8 bits, and 16 bits, with a non-quantized version of Langevin dynamics, so which is referred to LSD star. And basically, you can see in the figure on the right that actually we achieve with QLSD, so the curve in green, we achieve actually the same mean square error as LSD in red by actually transmitting roughly 3 times less number of bits to the central server. And so actually we are more communication efficient than the standard Langevin stochastic dynamics. I also have here another illustration on Bayesian logistic regression, where I use QLSD++, so it is another instance of QLSD with variance reduction with this memory mechanism I presented to you just before. And again, we compare QLSD++ with 2 federated and distributed Markov chain Monte Carlo algorithms, so F-SGLD and DG-SGLD. And you can see that actually we have similar performances as these two existing and state-of-the-art federated learning algorithms. And basically, by comparing QLSD with its non-compressed counterpart, we also have a more efficient communication algorithm. And finally, we also had some experiments on Bayesian neural networks, and we compared actually the proposed algorithms, so QLSD++ and QLSD++ PP, where PP actually refers to partial participation, with a bunch of Bayesian federated learning algorithms. So you have actually the name of these federated learning algorithms. They basically we compared the proposed approach with these algorithms with a bunch of metrics, so accuracy, agreements, total variation with respect to the target posterior distribution, etc. And we have actually competitive results compared to the Bayesian federated learning approaches that use a communication scheme similar to federated averaging. So instead of using a compression mechanism, these existing approaches actually use multiple local updates in order to periodically communicate with the central server. So we can see that with these results, there is no clear consensus on is compression better than multiple local updates. So basically, it is not clear with the experiments we run. We just have some similar competitive results. And so this is the end of my talk, and I have some conclusion and perspectives regarding this work. So basically, we saw that QLSD tackles communication, data ownership, and data heterogeneity challenges, but there are also other challenges I mentioned at the beginning of the talk, such as improved privacy guarantees, such as with differential privacy. So we can think about a version of QLSD where we implement differential privacy by sending noisy version of the local gradient information, or by being interested in personalization. How can we personalize actually the global samples from the global posterior distribution? Also, we saw that QLSD is the stochastic counterpart of a deterministic algorithm, which is called QSGD, so quantized stochastic gradient descent. And can we actually build upon the main link between sampling and optimization by deriving a stochastic counterpart of the federated averaging algorithm? So basically, we are also working on this at Lagrange in Paris. And finally, we saw that QLSD suffers, as all non-adjusted Markov chain Monte Carlo algorithm, from the discretization bias of a stochastic differential equation. So standard technique actually in Monte Carlo methods actually is to consider a metropolis adjusting step in order to correct this bias. And so we can actually analyze theoretically a metropolis adjusted version of QLSD and see how it compares with the standard non-adjusted QLSD algorithm. So this is the end of my talk, and I thank you for your attention.
So thank you, Maxime. So I'm going to ask the audience if they have some questions related to the talk of Maxime. Okay, so I'm seeing one Q&A from Badruddin Noon. Of course, the others can either send me the questions or we can give them the floor to ask a question. So first of all, thank you. I have two questions related to a hardware cost of compute and sampling. Is the choice of the Q operator as quantized int block float purely motivated to reduce memory utilization and improve the communication bandwidth utilization, or are we also considering compute requirements? Okay. Integer are more attractive for low-power devices, simple hardware implementation, but are inferior to FP due to limited range. Some existing modem system on chips like QCOM, MTK do use FP16 arithmetic. I don't think the question is a bit clear, but it's mostly about your Q operator.
Yeah. So basically, I just presented actually a specific instance for the compression operator, so stochastic quantization one. But basically, the analysis and the approach I just presented actually is quite general, and actually you just have to assume to actually meet the following assumptions. So an unbiased compression operator and some bounds on the variance of this compression operator. So you can choose actually over compression schemes based on your specific needs and constraints, which actually meet these assumptions. And so basically we just used the simple stochastic quantization technique in order to have, because actually it has been used in QSGD, but obviously if you have over constraints, so you don't want to send some integers with alias encoding, you can consider over compression mechanisms and even actually biased compression mechanisms. So actually there are a bunch of papers on the use of biased compression operators. So I hope this answers a part of your question.
Okay, and the other question is, how does the distribution of the noise used for rounding impact the performance? Using Bernoulli for rounding is unbiased. Have you considered unbiased stochastic rounding where the noise is uniformly distributed, where the probability of rounding up or down depends on the distance from the floor?
No, actually, we didn't actually consider this setting, but it is a very interesting follow-up of this work. So basically, we just consider actually, actually, you can see that in the assumption, actually, I have a uniform probability to be active for each client at each communication round. So basically, we have in our theoretical part the possibility to have different probabilities to be active, so PK, but we did not create actually this probability with respect to the network topology or other constraints actually, but it will be actually a very interesting follow-up.
Okay, good. Are there other questions from the audience on the federated learning approach? So I have maybe a question, Maxime, is that most of the techniques that are using are mostly, I would say, supervised based, you know,
Yes.
for this federated learning. How can we come up, or are there any things done on this unsupervised approach?
Yeah, I think so. I think, I'm not sure actually, but there are some perhaps clustering based federated learning approaches where you perform actually clustering, so in an unsupervised way, but I didn't actually come up with some approach. Actually, I did not work on this topic, but it is very interesting. But because actually in practice, if you have mobile phones, but so basically the local data is not, it has a cost actually to label the local data. So basically in practice, you don't have your local data, which is fully supervised. So you don't have every label for if you have an image classification task on a mobile phone, actually it is too costly to label all these images. So it is actually a very natural follow-up of this work in order to extend actually this supervised Bayesian algorithm in non-supervised settings to meet actually businesses implementations.
Okay, very good. So I'm just checking. Are there other questions from the audience? And another question is, are you aware also of some kind of federated learning test beds which are available on which you can implement the kind of ideas that people are pushing for federated learning?
So you mean actually
I mean,
implementation of...
Yes, aware of initiatives of building federated learning test beds.
Yeah. So basically, there is actually a very nice federated learning GitHub repository, which is called Leaf as a Leaf, and basically it aims at gathering actually standard benchmarks for federated learning. So basically, you have benchmarks on next word prediction on mobile phones, for instance, image classification tasks, etc. And there is actually a huge community which actually aims at gathering all these data sets, and especially in personalization. So I mentioned this at the beginning of the talk. So basically personalization is very important, and basically there are a large, huge work on building this type of data set for personalized federated learning.
Okay, that's interesting. Okay, I don't know if other members have questions related to the talk of Maxime. In any case, I think I mean, you can contact Maxime for any questions you can have. He's quite available. I know him very well, and willing to answer questions you can have. And he's also continuing on this type of work. So let me thank you again, Maxime, for the time you spent on this talk. And we'll send you some questions offline. Okay.
Okay. Thank you, Marwan, and thank you all the organizers for this very nice seminar series. Thank you.
Thank you. Take care.
Bye.